Hi, my name is Donglin. I am a PhD student from UNC at Charlotte. Today I'm going to introduce our paper titled Efficient GPU Memory Management for Nonlinear DNNs. This is the outline of today's presentation. Let me start with the background and motivation. DNN has been the most popular research area in the recent years. Compared to the first well-known DNN model, AlexNet, which is proposed in 2012, the models now become much more larger. For example, the state-of-art vision model, Inception V4, requires around 45 GB, while AlexNet requires only 0.8 GB. It's 56 times more memory requirement. Unfortunately, the GPU memory growth rate is lower than what we would like. Between 2012 and 2020, the GPU memory only grows 8 times. Some proposed models, like AlexNet, do not fit on a single GPU. How are we going to train even larger models with the limited GPU memory? Before diving into the detail, we need to first understand what does a general deep learning program look like. Typically, a neural network is represented by combinations of tensors and tensor operators. For example, the connection of this neural network can be represented by two tensors. And people use API provided by a deep learning system to describe how does a neural network looks like in terms of tensor. The training process consists of two phases, forward pass and backward pass. In the forward pass, the input feature max, for example, X here, affect to the layer in the forward direction. Each layer processes the input data using the activation function. In the backward pass, the backward propagation computes gradients in the weight space with respect to a loss function. The backward propagation can only be performed when all of these required data structures are available on GPU. We also need to understand what tensors occupy the memory and their characteristics. In a DNN model, there are two major memory use cases. The first use case is model parameters. As the model parameters are not created by any operator, we assume they are in the CPU memory in the beginning of each iteration and are required to be swapped into the GPU memory before being used. And their memory can be reused unless their values are changed in the gradient update space. The second use case is the intermediate results, such as input feature max, output feature max, input gradients, output gradients. They are created by some operators. In our example, the operators include a convolution layer and input data, etc. For the intermediate results, when they are created, we only need to make sure there is enough memory to host them. But they are required to be swapped into CPU memory if the GPU memory is not enough to host them. We conduct a study with 4 representative neural networks to analyze the memory footprints of different neural networks, including AlexNet, VGG, RexNet, and Inception. From this figure, we can learn that more than 90% of GPU memory are used by feature max. The intermediate results, for example, feature max, are key factors for optimizing memory use for DNN training. And in this paper, we focus on the memory allocation for these intermediate results. Now I'm going to give a brief introduction on nonlinear DNNs. For linear networks, data is sequentially propagated in both the forward and backward passes. The training follows a fixed sequential execution order. Contrast to linear networks, nonlinear networks have a high degree of dependency variations. This is an example of nonlinear blocks from inception V4. There are join and fan connections. The fan connection creates 4 branches after layer 0. And the join connection, layer 9. Join results from these 4 branches in the end. Nowadays, the DNN could have hundreds of combinations of join and fan connections, making the neural network more complex. Memory swapping between GPU and CPU is one of the most popular techniques to reduce the memory requirement for DNN training. VDNN is the first which proposed to use 2 CUDA streams to complete communication and computation. With 2 processes, the CPU to GPU data transfer can be overlapped with the computation asynchronously. In the forward pass, the intermediate results from the preceding layer can be offloaded to the CPU memory and released from the GPU. Later on in the backward pass, this data can be brought back to the GPU memory before the propagation. Ideally, the performance can be maximized by hiding the communication by the computation time. VDNN enforces a synchronization barrier between layers. It means that the communication and computation stream cannot advance each other in both the backward and forward passes. However, this design made the performance really depends on the computation and communication ratio. It is a waste of computation resource if the communication time is the bottleneck. To demonstrate this issue, we ran an inception V4 and profiled the computation and communication time from 10 layers. From the profiling information, we can see that the computation time for layer 5 is much smaller than communication time. However, in the forward pass, it is not necessary to wait for the completion of offloading operation. Similarly, in the backward pass, the prefetch for layer 5 can be started as long as layer 6 prefetching is finished. A more efficient strategy is required to optimize the offloading and prefetching operations. After deciding the data to be allocated on GPU, here comes the next question: how to allocate tensor at a memory pool? The reason why we adopt memory pool to allocate tensor is that it can avoid the non-trivial delocation overhead from using the native CUDA API, for example, CUDA Matrock and CUDA Free. We use NVIDIA library CNMAC to allocate free tensor on the GPU, which requires 512, 512, and 124 megabyte GPU memory, respectively. Then tensor 0 and tensor 2 are free from GPU. From the log information, we can see that the available contiguous regions can be combined into a larger page in the same virtual space. However, the released region for tensor 0 cannot be merged with other available regions because they are not in the contiguous address. This before policy works well for linear networks. Here, white block represent the free region. If an incoming allocation request for tensor is 400 megabytes, for the linear network, it can serve the request because the combined region from the released tensor have enough space. However, for the nonlinear network, though there is 200 megabyte and 300 megabyte empty list, it cannot serve the incoming requests because they are distributed at 2 separate lists. Between these two fragmented space, the allocated tensors resides on the GPU longer than other tensor because it has higher reference cost. Fragmentation happens at the virtual address level. It is not allowed to modify the page table on the GPU, and it is also impossible to move data around the GPU with negligible overhead. Then let me introduce our system design and implementation. The goal of our proposed system diamond focus on two aspects. To enable the abilities to train various deeper and wider DNN models on the GPU. To achieve that, we optimize the operators, scheduling, and propose a dependency-aware swapping strategy. Secondly, we propose a unified memory pool to optimize the memory allocation for different tensors. Firstly, I will talk about what operators should be executed to reduce the memory requirement. Please note that the GPU can only process a single layer's computation at any time. So, given a nonlinear network, we need a memory-efficient approach to set up the execution order. Here we use the depth-first search algorithm to design the execution sequences for these nonlinear dependencies. Whenever there is a fault connection, we first explore all the executable layers in this branch. We finish these branches one by one and join their output in the end. The reason why DFS should be applied to construct the execution graph lies in two properties. First, DFS requires less memory space to reach the joint connection node in the nonlinear blocks when exploring the traversal path. Secondly, it can serialize the sequences of convolution layer in each branch. Then we should design when the data should be swapped in or out. We believe a good swapping strategy should overlap the computation with communication. Our solution is to propose a more efficient synchronization between computation and communication streams without barrier. After removing the barrier, it comes another challenge: how to balance memory saving and performance. For example, in the backward pass, if we prefetch too many layers, it does not improve the performance, but wastes GPU memory resource instead. Because the input features for poolings and activation layer are read-only data structure, we can start the offload operation for this layer when they are being propagated. As for computation stream, the next layer computation can be started as long as the previous one is completed, without waiting for the completion of the offloading operation for previous layer. Here's a case for nonlinear blocks. For example, residual blocks. It can benefit from this strategy because of the joint connections do not necessarily wait for the completions of tensor transfer from 1x1 and 3x3 convolution layer. At the end of each iteration, we use the CUDA stream synchronized API to guarantee the completion of computation for one iteration. And the release of those tensors is done by another individual thread. In the backward pass, prefetching the offloaded input feature max back to the GPU can be overlapped with the computation of backward propagation asynchronously. However, if the prefetched layer is too far away from the overlap layer, the memory saving benefit will be reduced because the prefetched data cannot be reused immediately, wasting the GPU memory. So, we restrict that no more than 2 convolution layers residing in the GPU, which is illustrated in line 11. This is because convolution layers are computation intensive. Prefetching this layer too early will underutilize the GPU resource. As long as it is not convolution layer and not available yet in the GPU memory, it can be chosen as the candidate, as shown in line 14. This is because other layers require shorter computation time. Last but not least, how should we allocate a tensor? We believe an efficient memory allocation results in less fragmentation. We propose a contiguity-conserving memory management solution. The goal is to minimize the unusable free space. We defined the unusable free space as how much of the available free memory cannot be used to satisfy an allocation. Here, the right item is the desired allocation. Total free represents free space. A term of 0 implies there is no memory fragmentation, and a term tending towards 1 implies high fragmentation. And our goal is to reduce the memory fragmentation. We consider splitting the memory space into 3 areas. Tensors are placed such that each area contains tensor of the same page mobility types. For movable tensor, they can be released after being propagated, and the release space could be combined with others soon. Temporary tensors exist longer than movable tensor and are not supposed to be mixed with them. Specifically, I want to talk about recurrent tensor here. Tensors from those layers are not selected for offloading. This figures demonstrate the fraction of memory usage by various layers for different networks. We can learn that the memory usage of convolution layer, activation, and pooling layer batch normalizations can account for more than 90% of total usage. However, it is not fruitful to offload dropouts, softmax, and fully connected layers because they are only require less than 1% of the total memory. This layer requires less memory, however, it still requires us to manage the allocation for this tensor carefully. Otherwise, it can cause further fragmentation. So we classify this layer as recurrent tensor. And let me give you a toy example to introduce our solution. First, we request a memory pool based on the approximation. If an incoming tensor has one reference count, we classify it as movable tensor. The allocations starting from the low end available space, following the default best fit here listed. If the tensor has no reference, it can be released from the memory pool, and the free space will be merged with other available spaces. If an incoming tensor has more than one reference, we classify it as temporary tensor. The allocation starts from the high-end address, pointing to starting address to the high end. If inside the nonlinear box, there is another fan connection, and we suppose it has 2 reference counts, we allocate it from the high-end available address. So, with the propagation going on, the reference counts for each tensor in the high end will decrease in an opposite order with allocation. As a result, the allocation is in an opposite order with allocation. As for recurrent tensor, we use the default CUDA macro to request a new GPU memory outside of the existing pool. Though this procedure will cause initialization overhead, it is negligible because of the minimal proportion of this layer in the neural networks. Because the backward propagation follows the reverse order of forward paths, the allocation is from the low to high end, while the delay allocation is from the high to low end, leading to no fragmentation. In summary, we divide the memory space into main and incremental areas. Inside the main space, the allocation can be started from both the low and high end available objects, and the allocation area is based on the types of tensors. Here comes the evaluation section. Our experiment evaluation is performed on a GeForce Titan X with 12 GB GPU memory. We compare our system performance with DNN and superneurons. Specifically for superneurons, we only enable the liveness analysis and unified tensor management components because lead computations is not considered in our work. We implement both linear networks and nonlinear networks. Specifically, we validate the backsign and depth for LexNext to validate that our systems can support wider and deeper neural networks. Because the GPU memory uses dual forward-backward paths, will fluctuate depending on the tensor chosen for offloading and prefetching. So we report aggregated memory to represent the memory, the maximum GPU requirement for one iteration. It is also the minimum requirement to train the networks. From the results of linear networks, VGG16 and AlexNet, we can see that there is no difference between these three strategies. For VGG16, our system even requires nearly 250 megabytes more memory capacity than DNN for AlexNet, because Dimensions aggressively prefetch one more layer data structure in the backward path than VDNN, trading the memory space for performance improvement. For in section B4, the maximum memory footprint is reduced from 3600 megabytes to 2500 megabytes, resulting in 31% memory saving compared with DNN. And we also present the end-to-end training throughput comparison of Dimax to DNN and superneuron. The training throughput is measured by the number of processed images per second. We validate the batch size for different DNNs and compare the corresponding throughput. For linear networks AlexNet, there is not much performance improvement over VDNN and superneuron because these networks are composed of simple and sequential layers. The performance for nonlinear networks, for example, the inception results from the can be achieved from improving the communication and computation ratio, because Diamond can better utilize the bandwidth of PCIe. We can also observe that the throughput has slowly deteriorated by increasing the batch size. This is because GPU memory can only accommodate less network layer with wider networks. So it could result in the decreased communication and computation ratio. There are existing works proposed to optimize the tensor swapping for large models. For example, VDNN proposed to swap intermediate results tensor layer by layer. And there is another paper proposed to use a near optimal way to swap the memory automatically. However, it is only limited to linear networks. And superneurons combine swapping and lead computation strategy. And I want to mention that lead computation strategy can be orthogonal to our work. And in conclusions, we present Dimax to find a good operator schedule and memory allocation for swapping, and results so that it can achieve good performance for different types of wider and deeper network. And thank you. That's all my presentation.